Is Rachel?
Yeah.
Rachel King. I know Rachel. Brandy. This Rachel. Becky. Brian Crummell. Henry. Alexia. Caleb.
Professor Harris, so when a fixed point, say a limit, is coming from both sides, that's a fixed limit, right? That's what you would
If
call
x
it?
approaches a certain number and the y goes to the same value, that is the limit
Right.
as x approaches a.
As it's defined.
Yes.
But then if it's coming, say, from the right or the left side, it's called is it an indeterminate? What is that phrase?
If they approach two different values, like if you had a piecewise function as x approaches a, if one goes to one number and the other goes to a different y value, it does not exist.
Right.
If it approaches different numbers from the left and right.
Okay. But if it approaches just from one side and has a limit, that is called what type of limit again?
Well, last time we had defined the left-hand limit
And the right.
and the right-hand as x approaches a from the left,
Right.
or if x approaches a from the right.
Right.
Like today on the quiz, I didn't give you left or right, I just gave you
Right.
plain old limits.
Okay.
Yeah.
But okay.
I mean, were there specific homework questions that you had trouble with? Or?
Well, I'm just trying. I wanted to make sure I had that in my process. I did the homework and I didn't have a lot of problems with it, but I just wanted to make sure I had that in my thinking.
Okay. Any other homework questions? We still have a couple of minutes before 2, but glad to look at them. From any of those sections that you studied for the quiz?
Page 14, page 72. I didn't get the section 42.
10, what page? 72.
72, yeah. 72.2. 72, number 45. 40, 43 to 46. Pretty much that's it.
Okay.
Wait, no.
Well, if you did 45, alphabets was 416 squared. They ask you to find this. Okay. So that just means take this function and plug this here. And work it out. And then plug a here and subtract them. So I'll say 4 minus a plus h squared minus 4 minus a squared. And I'll have to put this in parentheses. You see what that's saying? First put in a plus h and work it out. Then subtract, plugging in a. And that's going to give me 4 minus a squared plus 2ah plus h squared minus 4 plus a squared. 4 minus a squared minus 2ah minus h squared minus 4 plus a squared. Do you see that the a squareds would subtract out? The 4s would subtract out? And you're left with negative 2ah minus h squared, I believe. And that's all you would need. Is that okay?
Kind of not.
See, this is going to make a lot more sense after next time. They're trying to get you used to this expression because we're going to define this. The limit as h approaches 0 of f of a plus h minus f of a over h. And that's going to be our definition of derivative. So they're slowly trying to get you used to expressions like that, to get you used to this definition. And I guess they're not succeeding in that. So, but this just says, you know, if this is f of x, if you know how to find that, whatever's in the parentheses, you plug there, don't you? And then whatever's in this set of parentheses, you plug there, and then I'll just subtract the two because I'm subtracting those two. So I plugged in a plus h, and I got this. Then I plugged in a, and I got this. And then I subtracted. That's all that is. And that's not something that's important on today's quiz or anything. What's important from that section is the F composed with G.
So,
Okay.
page
Thank you.
112.
112.
Fifty-nine.
59. Says the limit as x approaches 1 of square root of x minus 1 over x minus 1. Okay? And they ask you, they give you a hint and they say multiply by square root of x plus 1 top and bottom. If I do that, upstairs, look what it gives me. It would give me x minus 1 when I distribute. And this gives me x minus 1, and that I'm going to leave it undistributed because then I can cancel that. And if I plug 1 in now, I get 1/2, don't I?
Yep.
Okay?
That's what I was getting.
That was just using some algebraic trickery so that the x minus 1s would cancel. And then you could actually evaluate that limit. Because once they cancel, this is just a 1 up here. And if I put a 1 there, I get 2, don't I? So that makes it nice. But that's not obvious, is it? Unless they gave you that hint. So, like I said, if it's ever that indeterminate form, you've got to do something algebraically trying to evaluate that. Or graph it and see what happens. See if you could approach it. You would see if you graphed it that as x gets close to 1, the value of y gets close to 1/2. So, okay. Any others? Those are good questions.
73.
73. Did Brian come in? And Rachel King? No.
Actually, 78.
78? Okay. On 113? Now, remember, that was the type. 78 was the type we said the limit as x goes to infinity of 4x to the 4th minus 3x squared plus 1 over 2x to the 4th plus x cubed plus x squared plus x plus 1. What did I urge you to do if you have an infinity limit and it's a rational function like that? Didn't we say divide everything by the highest power of x in the denominator? Remember that? So if I do that, I'm going to divide everything by x to the 4th and then look at it. Now that's going to leave me 4 minus 3 over x squared plus 1 over x to the 4th over 2 plus 1 over x plus 1 over x squared plus 1 over x cubed plus 1 over x to the 4th, right? All of these go to what? All of these fractions, if x goes to infinity, all of those go to 0. So what's my limit? 4 over 2 is 2. That's a perfect example. It looks horrible, but really it's not, is it? Because if you divide everything by x to the 4th, all that's left is 4 over 2. Everything else goes to 0 as x goes to infinity, or negative infinity. So
47.
47. On 112?
Yes, sir.
47 says the limit is x goes to a 2f of x minus g of x over f of g of x. Okay. The instructions say find the indicated limit given that the limit as x approaches a of f of x is 3, and the limit as x approaches a of g of x is 4. Okay? I think they just want you to use those properties to where I could take the limit of numerator over limit of denominator. Remember that from our little chart of limit properties? And if I do that, the limit of this I could separate into 2 times the limit as x approaches a of f of x minus the limit of g of x. Well, I know that. Up there, that would be 2. The limit as x approaches a for f of x is 3, so that would be 2 times 3 minus 4. And downstairs, the limit of that product would just be the product of the limits. So is that 6 minus 4 over 12? 2 twelfths, is that 1/6? Just using those limit properties that are in that box on page, where is that box? 102? 102? That's just using several of those in one problem. Limit of this over limit of this, and then you can separate it into limit of this minus limit of that. Bring the 2 outside, and then you've just got those values. Any other questions? Okay. So what's the quiz over? It's over f composed with g, composition of functions. It's over cost, revenue, profit, supply, demand. Studied some of those like you went through this class. From 2.3, and then 2.4 that we were just doing some examples of on limits as x approaches a, limits as x approaches infinity. Yes. If f of x is x squared plus 1, and g of x is 2x, what would be f composed with g of x? Doesn't that mean f of g of x? Put this inside that. So that means f of 2x. I'm going to put 2x where? Right there. So that's going to be 2x in parentheses squared plus 1. So what's my answer? 4x squared plus 1. Is that okay? Putting g inside f. Now, if it said g composed with f, I would put f inside g. If I switched it, g composed with f of x, that would mean g of f of x. And that would mean put f of x where? Inside g. And that answer would be, if I put the x squared plus 1 inside there, 2 times x squared plus 1, 2x squared plus 2. That would be G composed with F. Putting this one inside that one. Putting this one inside that one. And working it out. Okay?
Would you mind working out 77 on 113?
77 says the limit as x approaches negative infinity of x to the 4th plus 1 over x to the 3rd minus 1. What would I divide by?
X to the 3rd.
The highest power of the denominator is x cubed, isn't it? So if I divide everything by x cubed, this is going to give me a good picture of what it's actually doing. Well, this gives me x plus 1 over x cubed, 1 minus 1 over x cubed. Is that right? If I reduced, what do these go to? These go to 0, don't they? 1 over x to any power, if x goes to infinity or negative infinity, goes to 0. So those are gone. All that's left is x over 1. Well, if x goes to negative infinity, and you have that x, where does it go? Negative infinity. And that makes sense, doesn't it? Because if this was 1 power higher than this numerator and that denominator, that means if you disregarded everything else, that's really going toward x, isn't it? And x is going to negative infinity, so that's going down forever, isn't it? That's decreasing forever. So, okay. But a better question is if this would have been an x to the 3rd here, what would you have answered it then? 1 over 1 would be 1. Yeah. That would be a more interesting question. Okay. Any other questions? Those are good. All I really want to do today is try to finish 2.5. Last time we started 2.5 and defined the one-sided limits, the left-hand limit and the right-hand limit. And I need to give you one other definition to finish this section. Okay? After today, after 2.5, I only do half of 2.6, about 6 problems, and we're done with the unit. So I'm thinking on Wednesday, we're going to finish the notes and review half the period. So it's not like I'm going to just jam a lot on you on Wednesday and then throw the test at you Monday. We're going to have just about half the period to finish our notes, and then the other half I'll tell you what to expect and how to study for it and everything. And I think that'll work. And I know you think, oh, I wish we could have more time, for the test. I swear, if we don't start moving a little faster, at the end we have to start rushing and finish that syllabus, and you don't like that. I don't like that. And I don't want to make you rush through like the integrals when we get to it, the antiderivatives. And the more time we have, the better. You'll be glad. So I think it'll be just fine. So, but let's do this, and then we'll take our quiz at the end today. Go back to page 127. Hopefully, if you haven't tried up through 37 yet, do that tonight and tomorrow night. But I need to finish this section with a real important definition of a term called continuity. Let's define continuity. Let's see. Let's define a continuous curve. And I wish that would just go away. Here we go. A smooth curve that has no gaps or jumps, an unbroken curve. That's very clear. This would be continuous, wouldn't it? But if I gave you something like a piecewise, where this was one piece, and then the other piece picked up into that, that's not continuous, is it? That's broken. That has a gap in it. Okay? Even something like this. What if I erase, and Mr. Bryce put all my erasers over here? Pet peeve.
I don't know, purpose.
He does that just to get me to. even if I had that original one and I put a hole in it, is that continuous now? No, it has a gap in it. It has a hole. Not continuous. So, that's the definition of a continuous curve. What if I just gave you an equation or a function and I said, is it continuous? It has to meet these three conditions, just like a cookbook, okay? A function is continuous at x equal a if and only if, and look how easy these are. If f of a exists, so if you plug in a in your function, and you get an answer, 1 and check, done. The limit as x approaches that number a exists. Can I find the limit as x approaches a? We'll find it. And are those two equal? That's the third condition. Is that equal to that? Those are easy, aren't they? What's f of a? What's the limit? And are they equal? Check, check, check. Yes, it's continuous at that point. Okay? So what we could say is, what if I fill that dot back in and this was continuous again? If I said at that point, if this was my a, the limit as x approaches a is whatever that y value is. Right? F of a is that y value. They're equal, aren't they? F of a is this point. The limit as x gets close to a is that value. So since they're equal, it would be continuous at a. What would you say about this one if this was a? F of a might be that closing circle, but the limit as x approaches a from the left is here, from the right is that open circle. That failed, didn't it? The limit does not exist as x approaches a. They don't go to the same number for both sides. So you would say, no, not continuous because condition 2 failed. And I'll probably ask it like that. Is a certain function continuous at a point? If so, show me all three of those are met. Otherwise, tell me which one fails. And usually it's very easy to find. So let's just do a few examples using those. On page 127, do you see number 40? 40 says, they give you that graph. Does everybody have their book and can see it? Okay. Do you see that 40 is basically a parabola with an open circle and there's a dot at the origin? Okay. So what they're asking you, and they give you the function. They say 40 is this function. It's this parabola if x is not 0. And it's 0 if x equals 0. Okay? The question is number 40, are there any discontinuities? Are there any points where you think it's discontinuous? Yeah. I would say any place that it seems to break in a piecewise, I would need to test. So my question, continuous at x equals 0, question mark? Well, first tell me, what is f of a? What's f of 0? F of 0 is 0. That's fine. 2, what is the limit as x approaches that number 0? If I get closer and closer to 0 from both sides of this, that goes to 1, doesn't it? So what fails? 0 is not equal to 1, is it? These are not equal. So you say this fails. Condition 3, not continuous. Not continuous at 0. You could have looked at that graph and told me that there's an open circle with a dot below it, right? You saw there's a gap in there. You know it's not continuous, but why? Well, that existed, but they weren't equal. Condition 3 failed. Okay? That's what they're getting at here. Why? You see from the picture that it was not continuous, but why? Okay?
And also equal 0 doesn't equal 0.
Right? Well, if you plug in 0, that was this leg, this branch of it, right? That piece. The limit, I had to use this piece as I approached from both sides, and it went to 1 from both sides. But this value is not equal to that limit. So since they're not equal, condition 3 fails. would you say about 42? Do you think there's any problems there, or does that look continuous everywhere? Do you see any gaps in that graph? Any breaks? I don't see any. So what do you answer 42? Continuous everywhere. That's the way we would say it. Continuous everywhere. And they gave you the function, the absolute value of x minus 1. You might say, well, at 1, there's a sharp corner. Is that going to be a problem? Well, no. Because if x is 1, y is 0, isn't it? If you approach 1 from either side, it goes to 0, doesn't it? That v, to the point of the v. Since those two are equal, it's continuous at that point that I was worried about. So it's continuous everywhere. That's what we would say. Just looking at 44, what would you say about the point -1, if x is -1?
It's not continuous.
Not continuous. Why?
There's a big gap.
Yes. So you tell me, looking at that function, all right, in 44, if I said condition 1, what is f of -1? That's the second piece. That's 1, isn't it? The second condition, what's the limit as x approaches -1 of f of x? Well, if I look at my graph, as my function approaches -1 on the x-axis, where's the y going? Looks like down to that open circle, right? -2. So what do you say about condition 3? Fails. This was good, that was good, that limit, but these were not equal, were they? So that's why it failed. So how do you answer that question, 44? Not continuous at x equal -1 because condition 3 failed. Okay? Very good. All right, let me give you a few other little bits of information about continuity. I'm going to look at some examples. So we just said this. Those were our 3 conditions for continuity. I'm going to put this back, or it's going to write all over my notes. What did we say? If 1 or more conditions fail, f is discontinuous at that value. We saw that, didn't we? A couple of those, condition 3 failed, didn't it? Okay. If it looked like this, condition 2 would fail. The limit would not exist, would it? Approaches this value from the left and that value from the right. Okay. We say that a function is continuous on a whole interval of x values if it's continuous at every x value in the interval, at each x value. So I said this was continuous from -infinity to infinity, right? There was no break in it forever. Okay. I could probably say this one was continuous from -infinity to a, right? It didn't break till a, did it? Or it could be said continuous from a to infinity. But it's not continuous at a, is it? Okay. Here are just some other little, like I said, bits of information. If f and g are 2 continuous functions at x equal a, then the sum, the difference, and the product are continuous everywhere. That would be good. The quotient function f divided by g is continuous unless g of a is 0, which would make a 0 denominator. Makes good sense, doesn't it? This radical, nth root of x, is continuous everywhere if that index is an odd number like a cube root or a 5th root. But what would you say? If this is an even index like a square root or a 4th root, what do we not want under there? It wouldn't be continuous if there's a negative under there, right? So we say what? It's continuous 0 to infinity if that index n is even. So if it's a square root or 4th root, it's continuous 0 to infinity. But if that's a cube root or a 5th root, it's continuous everywhere. Okay? Makes sense, doesn't it? We don't want a negative under an even index radical, do we? And this one, this sounds like double talk, and I apologize for it. But g of f of x, like we were saying, our composition functions that we have on our quiz today, that's going to be continuous at x equal a if g of y is continuous at y equal f of a. In other words, if you put a into f and that value makes g continuous, it's fine. Otherwise, it's not. Okay, that's what we could say about that. All right, and this is my favorite one that's really helpful. Every polynomial is continuous everywhere. So when you look at numbers 45 and 46, what are those? They're polynomials. Where are they continuous? Easy. No question about it. No bad numbers. Continuous everywhere. Looks something like this, doesn't it? Maybe like a cubic polynomial. Easy, nice. And this one makes perfect sense, doesn't it? Every rational function is continuous everywhere except at points that make what? The denominator 0. So what would you say about numbers 47 and 48? Are there any numbers that make the denominator 0? If so, we would say they're discontinuous there. But I don't see in number 47, is there any number I could put in there to make it 0 downstairs? No, if I'm squaring the x, if I put negative 1, it would become positive 1. If I put 0, 0 plus 1 is still a valid number. There's nothing I could put in 47 to make a bad situation. So that rational function, continuous everywhere. No bad numbers. Where is 50 going to be discontinuous? What one number would make 50 bad? If x is 1, you got that 0 denominator. Fail that, wouldn't it? You know what? If you were saying number 50, is it continuous at x equal 1? Condition 1 fails. Because what is f of 1? Undefined, does not exist, does it? Condition 1 would fail. Okay? Tell me about 52. Let's look at that. F of x is x minus 1 over x squared plus 2x minus 3. Could you factor the denominator? How? Good. Now, even though we could cancel these officially, x equal 1 is still a bad place for that one, right? Because if I put 1 in there, it is undefined. It's actually indeterminate, isn't it? It'd be 0 over 0. But that's still a bad spot. So what two numbers would you say? You'd say discontinuous where? Continuous everywhere except at negative 3 or 1. Those are the bad spots that would make a 0 denominator. And even though I could cancel this one, there's still a hole in it when x is 1. Because you would think of this original format, and if I put 1 in, I'm in bad trouble. Because I got the 0 denominator. What would you be concerned about in 54 if you're given a piecewise function? 54 says f of x equals negative 2x plus 1 if x is less than 0, and x squared plus 1 if x greater than or equal to 0. Where would I be concerned that it might be discontinuous? Yeah, where it splits. At that 0 value where it splits, all right? Well, let's test it. If I said continuous at x equals 0, well, let's do the 3 conditions. What is f of 0? Which piece do I plug it in? Yes. If I plug that in here, I get 1. Second question, what's the limit as x approaches 1 of that function? If I come from the left and I get close to 0, what does this go to? If that gets close to 0 in this piece, it gets close to 1, doesn't it? It would wipe that out. What if you're coming from the right, from above? If you get close to 0, what does that go to? So it goes to 1 from both sides? So what do you say about step 3? 1 equals 1, so what do I say? Continuous at, where we tested, continuous at x equals 0. And everywhere, in fact, you're right. But we were just testing for that one x value that we were concerned about, where it's split. If these were not equal, I would have to say, not continuous, discontinuous. That's not too hard, is it? It's 3 conditions. Boom, boom, boom. What's f of 0? What's the limit as you approach 0? Excuse me. And are they equal? Okay. F of 0, limit as x approaches 0. Are they the same? Yes, yes, yes. It's continuous at that point. Okay. I guess the toughest one on that page is 56. 56 says f of x equals x minus 1, whoops, an absolute value over x minus 1. What would you say the problem spot might be? Yes. So we would say, is it continuous at x equals 1? Well, I guess it's not as hard as we thought, because what is f of 1? Or even you could say indeterminate, right? If you graph that, I just want to show you what the graph would look like. If I were to graph that, absolute, remember how to get to that? Math, numerical, number 1, absolute value of x minus 1, and then come out of that, divided by parentheses x minus 1. Minus 1. There we go. Look at this. See what happens at 1? If x is larger than 1, it's 1. If x is less than 1, it's negative 1. If you look at that graph, it breaks when x is 1, right? The limits are 2 different values. The one-sided limits. So that limit does not exist. And also, f of 1 did not exist. So the first condition failed, the second condition failed. They all failed. But I like that. What would you say about 58? Where's the problem in 58? What values of x would be discontinuous? Positive 2, positive 1. Make the 0 denominators. That would be it. And in 60, you would just have to factor out the x, and then you could look at what would make it 0. 0 and positive 2, maybe. Okay. 59, you would have to factor. 57, you would have to factor before you decided. Okay. 62, I think, is a good one. Do you see 62? The graph there has some discontinuities. Look at that graph. Do you see what this is representing? It says an office supply company orders 500 reams of photocopy paper every 20 days. It shows the actual inventory. Well, what happens? They have a lot of paper, then they use it. What happens? Starts to diminish. And after 20 days, what happens? Why does it go back up? They ordered. They ordered 500 reams, didn't they? Goes back up. Then they start using it, goes down. 20 more days, they order again, goes up by 500. That's all they wanted you to see. That's it. Okay? It said determine the values of t for which it's discontinuous. What would you say? At t equal 20, 40, 60. Very good. My favorite one, I'll let you do at home, number 63. I love that problem. Very interesting one. The only ones I want you to try from this section. Finish it. Now, I've already assigned the first part, but here's the whole assignment if you haven't done it yet. 1 through 59 odd in 63 and 65. That's the whole assignment, even though I signed up through 37 last time. Okay? Before we take our quiz, I'm going to show you how easy that little bit of notes we have to do Wednesday is going to be to finish up. Okay? Here's what we're going to define on Wednesday. Average and instantaneous velocity and rate of change. Okay? You know that average velocity, average speed that you go is what? The distance over the time, isn't it? What does this look like to you? Even though there are D's and T's. That's the slope formula, isn't it? So if I say what's the average velocity between 2 points, you find the slope between those 2 points. Look at that. If d equals f of t, the average velocity is the slope of the line connecting those 2 points. We all know slope, right? Okay. What if it's not a distance function? What if it's just a function y equal f of x? Then I wouldn't call it average velocity. I'd call it average what? Average rate of change. Slope. We know that. Okay? And there's the slope formula. y2 minus y1 raised to 2 minus x1. Okay? It's a little trickier when I try to define instantaneous velocity, and that's what I want to do next time. But would you all agree that if I gave you this distance function, if I said what's the average velocity between this point and this one, you could all find the slope between those two things. That's easy, right? Okay. So that's what I'm going to do next time. Just those definitions in instantaneous, and we'll have it done. You'll be ready for your test. Okay, I'm going to give you the rest of the time for the quiz. I don't think you'll need this long, but
Y'all be done early. Can we go ahead and work on that? That was the take home quiz today. Bring it back Wednesday.
what's that? What'd you say?
If everybody gets done in time for the quiz, could we go over some of 2.6? Go ahead, or
Yeah, I mean, but I promise, on Wednesday, I've just got these 2 little definitions left, which I want to take some time to explain, and then the rest of the time will be review on this, and I'll give you the take-home quiz for the weekend. It'll be good. Don't worry, it's going to be okay. Okay.
open those, right?
Open brain.